At 6,000 revolutions per minute, the space inside a cylinder is a volatile environment. A pressurized mist of fuel and oxygen is ignited by an electrical spark, erupting into an expanding fire front 50 times a second. The internal combustion engine operates as a heat engine. Its specific purpose is to capture the chemical potential energy stored in liquid fuel, release it through combustion, and force that expanding thermal energy to perform rotational mechanical work. Rather than viewing this machine as a mysterious black box, we will analyze it as a single physical concept, building the entire mechanism up from first principles. The engine block serves as a high-speed intersection of fluid dynamics, chemistry, and Newtonian physics working in continuous sequence. We begin with a blank slate, a single metal cylinder, a piston, and a crankshaft. In 1876, Nicholas Otto mapped out the four-stroke sequence that still defines this architecture today. During the intake and compression strokes, the piston creates a vacuum to draw in fuel and air, then compresses that mixture. At peak compression, the spark ignites the mixture, driving the piston downward. The final stroke clears the waste gases. This cycle is inherently parasitic. Of the four strokes, only the power stroke produces mechanical work. The other three consume energy to complete their functions. To maintain continuous operation, the engine relies on the rotational inertia stored in a heavy flywheel. This spinning mass provides the momentum necessary to push the piston back through the three non-power strokes. To manage the flow of air and exhaust, we seal the cylinder with a cylinder head housing dual overhead camshafts and precision machined valves. The camshafts use asymmetrical lobes to physically push the valves open. To synchronize with the four-stroke cycle, these shafts are geared to rotate at exactly half the speed of the crankshaft. We solve the intermittent power problem by expanding to a four-cylinder block. By staggering the firing sequence, typically in a 1-3-4-2 order, at least one piston is always providing a power stroke. This timing ensures that combustion events occur every 180 degrees of rotation, transforming isolated pulses into a continuous delivery of rotational torque. Operating at 6,000 RPM creates enough metal-on-metal friction to weld the engine internals together within seconds. Engineers use hydrodynamic lubrication to prevent this. Pressurized oil is forced into the bearing gaps, creating a fluid wedge. The crankshaft spins on this film of oil, avoiding physical contact. The engine also faces thermal overload. Only about a third of the fuel's energy is converted into work. The rest is released as intense heat. A liquid cooling loop absorbs this energy. A pump circulates an ethylene glycol mixture through the block and into a radiator, where the heat is dissipated into the passing air. This network of pressurized fluids is the only thing preventing the mechanical assembly from melting under its own operating temperatures. Maximum efficiency requires a stoichiometric ratio, exactly 14.7 parts air to 1 part fuel by mass. This chemical balance ensures there is enough oxygen to completely burn the fuel. Modern gasoline direct injection systems achieve this by blasting fuel at 3,000 psi straight into the cylinder during the compression stroke for ultimate precision. To increase power, we use a turbocharger. Hot exhaust gases, in red, spin a turbine. This drives a compressor, in blue, packing dense air into the intake. Routing this heated, compressed air through an intercooler drops its temperature, maximizing oxygen for the next combustion event. This process allows engineers to artificially multiply an engine's displacement and power output through pure thermodynamics. Coordinating these systems requires the Engine Control Unit, or ECU. It functions as a central processor that manages the engine as a reactive, closed-loop system. The ECU monitors a constant stream of data, including air mass, the intake pressure, the crankshaft position, and exhaust oxygen levels. High-performance systems, like the IV-Tech seen here, allow the ECU to use oil pressure to dynamically alter camshaft phasing. This optimizes valve lift and timing for both low-speed efficiency and high-speed power. The system also prevents damage through knock regulation. If piezoelectric sensors detect the frequencies of pre-ignition, the ECU instantly retards the spark timing to protect the pistons. The modern engine has evolved into a calculating electronic organism, making millions of micro-adjustments per minute to maintain its peak performance. Post-combustion, the exhaust gases pass through a three-way catalytic converter. Precious metal catalysts facilitate a reaction that converts toxic nitrogen oxides and carbon monoxide into nitrogen, CO2, and water vapor. We measure the results in torque, the twisting force that moves the vehicle, and horsepower, the rate at which work is performed. These two metrics are mathematically linked, always crossing at exactly 5,252 RPM. Different geometries offer different advantages. The boxer engine used in this Subaru WRX STI lays its cylinders flat. This horizontally opposed layout moves the engine's mass lower, improving the vehicle's handling. Every engine on the road is a calculated compromise between the chemical potential of fuel, geometric constraints, and strict emissions compliance. The industry is currently merging internal combustion with electric drivetrains. In vehicles like the Toyota Prius, the engine operates as part of a hybrid system, combining the efficiency of electric motors with the sustained range of liquid fuel. Future research into hydrogen combustion and carbon-neutral synthetic e-fuels suggests that the traditional engine architecture may adapt to a decarbonized world. The journey from a single thermodynamic cycle to a sensor-driven, fluid-cooled machine represents over a century of iterative refinement. The internal combustion engine remains one of our most successful engineering efforts, a century of design that converted the chaotic energy of fire into a reliable, synchronized source of power for the modern world.
For more Mechanism Explained, how things actually work, subscribe.